I'm going to do a short lesson here on a topic called summation. And this is in section 5.1 and a little bit of 5.2, but I just want to give you some notations here and show you what this means. You may or may not have seen this. If you saw this, it probably would have been in high school, maybe in Algebra 2. And if you've not seen this, that's okay. I just want you to see the notations here and understand what this stuff means. So we're talking about sigma, the Greek letter sigma, capital letter sigma. If you took stats before, you might have remembered hearing about lowercase sigma. That was used for standard deviation. But this looks like an E. This is the capital letter sigma. And we're looking at, when you see sigma, that means the sum of whatever those terms are. And so this notation, we would say the sum of a sub I, and I would go from 1 up to n. We would evaluate this by writing out term by term and adding them up. So we'd write out the first term would be a sub 1, the second term would be a sub 2, and so forth, up until we get up to a sub n, whatever that n is in the example. What do these terms mean? What would we call these? I, we would call the index of summation. Okay. N would be the upper limit. 1 in this case would be the lower limit, and it doesn't always have to be 1. Sometimes it's 2, sometimes it's 3, sometimes it's 0. Just depends on the function. And a sub I, we might call it the ith term. And by the way, I misspoke. I called it the function. Really, this is a sequence. So a sub I, we could also think of as a sequence of terms. The sequence would be a sub 1, then a sub 2, then a sub 3. We would list the terms in sequence up to a sub n. When we add those terms together, that's when it becomes a summation. And that's what the sigma is telling us to do. This is not as complicated as maybe it looks at first glance. Let's break it down and do some examples. So number 1, it says find the sum, and we're looking at, for part A, just I. So the series, or the sequence rather, is just I, and we want I to range from 1 to 6. This is a discrete series, 1, 2, 3, 4, 5. They go along like that. There's no partial terms. It's not continuous. It's just discrete terms, one right after the other. So if I is the notation and I starts at 1, we're going to have 1 plus 2 plus 3 plus 4 plus 5 plus 6. And so this would be the sum of the first 6 terms for this particular sequence. And I stopped at 6 only because 6 was the upper limit. So they wanted me to go from 1 to 6, and I'm getting a sum of 21. Let's try the next example. They want us to use I plus 1 as the ith term, but this time they want I, notice, to start at 0. So think about what these terms would look like. If I starts at 0, the first term would be 0 plus 1, and then 1 plus 1, and then 2 plus 1. And we're going to go up until we get to where I is 5 this time. And if you're observant, you might notice that this gives me the series 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's the exact same series as what I had in part A, just the notation is a little bit different. So the sum is still 21, but the route we took to get there was slightly different. How about letter C? Instead of I, they're using j squared, and they want j to range from 3 to 7. So we're going to have 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared. So we want the summation for the squares from 3 to 7. And I'm getting a total sum of 135. Lastly, we've got the term k squared plus 1 times 1 over n, and k ranges from 1 to n. Now, they didn't give us a specific value for n, but you're going to treat n like a constant. K is what's changing. Treat the n like a constant, because it would normally be a constant, where it would be the constant on top, just like it was in these other examples. So I'm going to write this out as 1 over n times, k starts at 1, so it's going to be 1 squared plus 1, plus 1 over n times 2 squared plus 1, plus 1 over n times 3 squared plus 1. Now, how do I know where to stop at? Well, I don't exactly. They said stop at the nth term, wherever that is. So I'm just going to say dot, 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 1 over n times n squared plus 1. So I don't have a definitive number for this because I don't know what n was, but I'm going to treat it like as if it was a constant. A couple of rules that go along with these that we're going to use and practice in class tomorrow. So the first one says that if we have a summation where we have a k, where k is a constant times a sub I, then we can put that k in the front. So we can always move constants to the front of the sigma if we need to. A lot of times that helps us make the rest of the calculations easier. If we are adding or subtracting terms, we can break them up into separate sigmas if that helps. If we have the summation of just k, so in other words, if k itself is a constant, the sum from 1 to n would just be kn. So for example, if I just had 3 and we ranged from 1 to 10, for example, what this rule says, because what would that be? That would be 3 plus 3 plus 3 plus 3 plus 3 plus 3 10 times, because it doesn't change. There's no variable, there's no index or I that's changing. So that would just be, or over here, that would just be 3 times n, which is 10, and the sum would be 30. And that's all that tells you. That's the like just adding up a constant. The next one says if you have I, so the sum of just I from 1 to n, that's going to be, you can calculate that as n times n plus 1 over 2. If you have the sum of the first n squares, I squared, that can be found using this formula here where you replace n with what's the number here. And finally, the sum of the first n cubes can be found using this formula right here. And we'll look at how to apply these formulas a little bit in class tomorrow.